Okay, so I think we can start with the introduction now. So yeah, thank you again for joining this session. Um, now this session is dedicated to the following topic: suppression of torque ripple for consequent pole permanent magnet machine by pole shaping method. And for this topic, I'm very happy to welcome G Key from the University of Sheffield, and I will introduce him to you. So GQ received the Bachelor of Science and Master of Science degree in Electrical Engineering from the School of Electrical Engineering, Southeast University, Nanjing, China in 2016 and 2019 respectively. He's currently working toward the PhD degree in Electrical Engineering at the University of Sheffield in the UK. His current research interest is the design of high-performance hub machine of electrical vehicle. So as usual, during this session, you will have the possibility to ask questions using the Whova or the Zoom platform. We will collect all the questions and answer it by the end of G's presentation. So Giz, I think you will be able to share your screen now.
Okay. Sorry, I can't share my screen.
Yeah, give me 1 minute.
Yeah.
It should be okay now. Can you do it again?
Yes. Can you see my screen now?
Yes, I can see your screen.
Okay, great. So now let me start. Good morning, everybody. My name is Ji Qi from the University of Sheffield. My supervisor is Professor Ziqiang Zhu. And today, my topic is the suppression of torque ripple for consequent pole permanent magnet machine by pole shaping method. So here is the content. In today's topic, I mainly introduce two parts, including the symmetrical pole shaping method and the asymmetric pole shaping method. So now let's start with the introduction. Firstly, let me introduce the consequent pole structure. It comes from the conventional structure like the SPM machine shown in the left side. By replacing the alternate magnet with the iron pole, we can get the structure shown in the right side. This is the consequent pole structure. The black dashed line shows the flux path under one pole pair. In the flux path, it is clear that the magnet potential is halved, but the magnet reluctance is also almost halved. That means the flux linkage can be almost the same. So that's why it can maintain an almost the same average torque, while have the advantage of cost reduction, including both fabrication and maintenance. Also, due to the reduced flux reluctance along the flux path, it will lead to a higher inductance. So it can achieve better flux weakening performance for this structure. It is also reported that this structure can achieve lower eddy current loss in the magnet. So that's why it has been widely used in many kind of machines, like hybrid excited machine, Berlitz machine, vernier machine, CPPM machines, and so on. And also, this kind of machine has many applications, like electric vehicle, rope-less elevator, pumps, compressors. However, this structure also has its drawback. In this structure, the even order harmonics will exist in the back EMF and cause serious odd order torque ripple, especially for the third order torque ripple. Here is a brief literature review. It has been verified that the wider magnet pole arc to pole pitch can achieve higher torque, average torque for this structure. So this will lead to the asymmetric pole parameters on the north pole and the south pole. So it will lead to the serious third order torque ripple. To reduce this, the torque ripple, there are mainly three methods. Firstly, is slot pole number combination. when the slot pole number combination satisfied with this formula, the torque ripple for the consequent pole structure can be reduced to the level of their SPM counterpart. This is because when the slot pole number satisfied with this formula, there will be the opposite phasor coil allocated into one phase. So the compensation effect can be utilized to reduce the torque ripple. However, this method is limited by the slot pole number combinations. The second method is the modular structure. This includes both the axially modular structure and the circumferentially modular structure. However, for the axially modular structure, it is quite complex. And for the circumferentially modular structure, they are also limited by the slot pole number combinations to some extent. The third method is the rotor shaping. However, for all of these works, the fundamentally different natures of PM pole and ion pole are not meaningfully taken into account. Actually, due to the different features between the magnet pole and ion pole for the consequent structure, it will cause the unbalanced positive and negative waveforms in the air gap flux density, and this will lead to spatial even order harmonics. According to those formula, the unbalanced flux density will lead to the different pattern in the Coggin torque. For the SPM machine, the Coggin cycle number in a mechanical cycle is the least common multiple of slot number and pole number. However, for the consequent pole machine, it is the least common multiple of slot number and the pole pair number. Also, the even order harmonic in the flux density will in turn contribute to the even order harmonics in the phase linkage and hence the even order harmonics in the back EMF. So to suppress the torque ripple, we need to suppress the even order harmonics. Subject to the constraint of a fixed amount of each magnet segment and introducing the flux gap at the end of each magnet segment as feature to reduce the flux leakage, the optimum pole arc ratio tend to decrease slightly from that established in the previous paper. In the previous paper, the optimum magnet pole arc ratio is around 1.2. Also, we can find that the flux density under the magnet pole is governed largely by the magnetic potential of PMs, while under the ion pole, it is mainly governed by the air gap magnetic reluctance. So from these two formula, here, the LMP and LIP are the functions of the pole shape. We can see that they are in the numerator and the denominator for the flux density under PM pole and ion pole respectively. So that means the adoption of different shape for these two pole types is likely to yield some performance dividend. To verify the principle, here, the genetic algorithm is utilized to optimize the structure. And in this study, a 12-slot 8-pole number combination is utilized as example. Here, the pole shape is defined by 7 discrete points uniformly distributed over each half pole, and the curve is used to connect those points to form the profile. And in the optimization, the variables are the radius of those points and also the pole arc span. The fixed parameters are listed in this table. And here we have two objectives. The first one is to maximum the torque only, and the second one is to maximum torque at reduced torque ripple. So here are the machines that will be compared in the following part. Firstly, it is the conventional SPM machine. By directly replace the alternate magnet with the ion pole, we can get the CPM 1. And under the same amount of magnet, by changing the pole arc ratio, the pole arc span, we can find a point that can achieve the highest average torque. So for this structure, I call it CPM 2. With the help of the optimization, we can find a structure that can achieve the highest output torque. Here, I'll call it CPM 3. And also, with the help of the optimization, the objective is to maximum torque at reduced torque ripple. So with the trade-off between the torque ripple and torque, we can find a point. For this structure, I'll call it CPM 4. So next is the performance comparison for these machines. And here are the models in the GMAG designer. This slide shows the comparison of air gap flux density, flux linkage, and back EMF. From the spectra, we can see that for the CPM2 shown in the purple bar here, it has the highest even order harmonics, which in turn will result in appreciable torque ripple. And for the optimized CPM4 shown in the red bar here, it can reduce the even order harmonics very effectively, which verifies the utility of the proposed optimization method model. Here shows the comparison of the cooking torque. Here we can see that from the spectra, the cooking torque harmonic orders for SPM machine shown in the green bar here are the multiple of 6, while for the consequent machine, they are the multiple of 3, which is the same as the previous analysis. For the CPM2, which can achieve the highest output torque, it has the largest cooking, since it has the largest harmonics, as shown in the previous slide. And for the CPM4, it exhibits the lowest cooking torque due to the smaller harmonic. Here shows the rated torque comparison for these machines. Firstly, let's look at the PM utilization ratio here. It is obvious that for all of these consequent machines, they exhibit significantly higher magnetic utilization ratio than the SPM counterpart. For the CPM3, it has the largest output torque due to its flux gap in the rotor and the relatively smaller equivalent air gap length. For the CPM4, the optimized CPM4 with the symmetrical pole shape, it has the smallest torque ripple. And shown in the right side, it is obvious that for the optimized CPM4, we have different pole shapes for the north pole and the south pole, or I mean the magnet pole and the ion pole. So that validates the analysis. Here is the torque performance on the different load. As shown in the red line here, the CPM4 can achieve the lowest torque ripple among all working conditions. And shown in the blue dashed line here, the CPM3 can achieve the highest output torque under the overload condition. And also under the overload condition, the output torque of CPM4, shown in the red line here, is higher than that of CPM2, shown in the purple line here. It was mentioning that this trend will be reduced under the rated condition. This is mainly results from the larger equivalent air gap length due to the pole shapes for CPM4. Here is the losses and the flux density distribution comparisons for these machines. The consequent machines have lower losses, and also The CPM4 shows the lowest value for both core loss and the PM eddy current loss because of the smaller high order harmonics and the lower saturation level. So now let's make a brief conclusion of this analysis. The different PM and ion pole shapes and approximately equal magnet pole arc span and pole pitch are necessary to achieve both the largest output torque and low torque ripple for a fixed amount of magnet. For CPM3, the approximate square shape of PMs can increase the fundamental air gap flux density, and the flux gap adjacent to the size of the magnet are effective in reducing flux leakage. And for the optimized CPM4, it has a symmetrical pole shape here. The modified shapes can achieve low harmonic in flux density, especially for the even order harmonic, and consequently Cogging torque ripples, and the losses can be reduced. However, here there is a very strange phenomenon for our symmetrical pole-shaped machine CPM4. As shown in the left figure, we can see that it seems like a virtual wall here, and the torque ripple cannot reduce any further. However, it should be effective. The pole shaping method should be effective in the conventional SPM machines. So this phenomenon is quite strange. That's why I try to analyze the asymmetric pole shape in the following part. It is commonly agreed that the asymmetric pole parameters will cause even order harmonics in back EMF, and this will lead to serious odd order torque ripple. However, in all of these papers, the role of reluctance torque ripple has hitherto not been addressed. Actually, in this paper, it analyzed the consequent pole inductance. Here, it is very obvious that in the self-inductance, the first order harmonic is very large, which doesn't exist in the conventional structures. The odd order in self-inductance will cause odd order harmonics in DQ axis inductance, and this will lead to large reluctance torque ripple. To make it clear, we can separate the overall torque into three components: the PM excitation torque, reluctance torque, and the Cogging torque. For the first formula, it is the PM torque. We can see the PM torque is directly related to the flux linkage, that is the psi, and the odd order harmonic in the psi DQ will lead to the PM torque ripple. That is the same as the previous analysis. And for the reluctance torque, as shown in the second formula here, it is directly related to the inductance waveform. Let's suppose the mutual inductance is 0 for our consequent pole machine, and we just consider the DC part and the first order harmonic in the self-inductance. We can find that it will lead to a large third order harmonic in the DQ axis inductance. This will cause the reluctance torque ripple. And this is mainly caused by this structure. As shown in here, for the consequent pole structure, we have only one salient pole in one pole pair. So that's why it has a large first order harmonic in self-inductance and causes the reluctance torque ripple. So no matter what the pole shape is here, it can only reduce the harmonics in the flux linkage. That means we can only reduce the PM torque ripple, and the reluctance torque ripple is almost unchanged. So now that we can't reduce the reluctance torque ripple by pole shaping method, so here I come up with an idea. We can introduce the PM torque ripple again and make it counteract with the reluctance torque ripple. so that we can achieve the overall torque ripple is very small. To achieve this, the asymmetric pole shape is necessary, since with the help of the asymmetric pole shape here, the asymmetric flux density can make the faces of each harmonics more flexible. That's why the asymmetric pole shape has the potential to reduce the total torque ripple by manipulating the faces of PM and the reluctance torque ripple. To verify this idea, the genetic algorithm is also utilized here, and the both symmetrical optimized shape and the asymmetric pole shape are optimized to verify the principles. Similarly, the variables are the radius of 7 discrete points uniformly distributed over each half pole or whole pole. And the fixed parameters are listed in the table. And for this time, the objective is maximum torque at reduced torque ripple. Here shows the results of the optimization. The optimized model with the symmetrical pole shape, I'll call it model A in the following part. And the machine with the asymmetric pole shape, I'll call it model B in the following part. For comparison, the conventional one is also set here, which can achieve the highest average torque with this pole arc span. In the following part, there are the performance comparison for these models. And here are the models in the GMAG designer. This is the comparison of air gap flux density and back EMF. We can see that the amplitude of even order harmonics in model B, shown in the green bar, is larger than those in model A, shown in the purple bar here, which is because the asymmetric air gap or EMF waveforms in model B. Also, the angles for even order harmonics for symmetrically shaped poles of model A and the conventional model are the same as shown in the left and the right side. And in the middle part, for the asymmetrically shaped model B, they shows the different angle. Next is the rated torque comparison. Here, to separate the torque components, I used the frozen permeability method in GMAG. I have to say this is a very good function. And in the model here, I freeze the permeability of the rotor core and stator core. Here are the results. Here, firstly, we can see that the average torque for pole-shaped machine is slightly lower than the conventional machine due to the larger equivalent air gap length. And let's look at the torque ripple shown in the black line here. For the conventional machine, it has a very large torque ripple. And for the model A with symmetrically pole-shaped machine, the total torque ripple can be reduced, but is still relatively large. And for the model B with asymmetric pole-shaped model, the torque ripple, the overall torque ripple shown in the black line here is very small. To make it more clear, I try to plot the phasor diagram for the dominant third order torque ripple. As shown here, the model A, we can see that the model A has the smallest PM torque ripple among the three machines. And for the model B, with asymmetrically shaped magnet, the angle between the reluctance torque ripple and the PM torque ripple is close to 180 degrees, resulting in near cancellation. And once the contribution of the Coggin torque phase is added in, an extremely small third order total torque ripple is achieved for model B. And also for the conventional one and the model A with symmetrical pole shape, here the red line and the blue line have almost the same direction. This is because they are both symmetrical shaped machine. This slide shows the torque performance under different load. Under no load condition, it is the Coggin torque. And here, the model A with symmetrical magnet shaping produces the smallest peak-to-peak value of Coggin torque due to the most balanced flux density. And for the model B, it has a relatively larger Coggin torque, and this leads to the marginally higher torque ripple on the light load condition shown in the green line in this figure. The torque ripple for model A and model B improve significantly with the increase of current. This is because the reluctance torque is proportional to the square of the current, while PM torque is proportional to the current. But overall, this shows the lower torque ripple than the conventional one. Here is the performance comparison of the loss and flux density distribution. The predicted ion loss and the two optimized machine are lower than that of conventional machine under the rated condition. This is mainly because of larger equivalent air gap and the reduced air gap field harmonics for two shaped machines. So now let's move to a brief conclusion of the asymmetric pole-shaped machine. In this report, the dominant third-order torque ripple for a 12-slot 8-pole consequent machine is illustrated as an example to be suppressed effectively by asymmetric pole shaping method. And in this report, the principle of manipulating harmonic phasors of even order flux density in air gap is demonstrated. Also, the results in the phasor movement of corresponding PM torque ripple and Coggin torque harmonics, and thus leads to a high degree of torque ripple cancellation are verified. What's more, the lower Coggin torque and the lower ion loss can also be achieved by the proposed machine. Okay, that's all. Thank you.
Thank you very much, G, for your very nice presentation. It was very interesting to see how pole shaping can be used to reduce torque ripple. We have some time to cover some questions from the attendees. So that's great. And to those who have not asked their question yet, it's still time to do it on the Zoom, on the Q&A panel, or on Whova as well. So to start, G, we have two questions related to maybe the same topic. So I would maybe ask them to you at the same time. The first one is shaping PM pole is interesting idea to reduce torque ripple, but how do you achieve this shape commercially? And the second question is PM shaping for torque ripple reduction is very interesting, but it increases manufacturing complexity and costly. What do you say in this regard?
Yeah, I think it's a very good, very good question. And I also thought about it in my research. Actually, if we just need a very small quantity of the machine, like we just need 1 or 2 prototype here, yes, I think it's quite costly and it's complexity, since we can only manufacture the shape like the shaped magnet from the standard shape, use some method like the wire cut. But I have asked this question to a friend who worked in international company, and he told me if we need a huge quantity of the machines, so we can change the manufacturing method, like use some mold or some other method So that means we can make the shaped magnet as a standard shape. So by this way, the cost of the manufacturing will not increase. They are almost the same as the conventional machine. So I think it has a commercial potential, yes.
Thank you, G, for your clear answer. Next question on a maybe different topic. Did you conducting a thermal analysis for this pole shape?
Actually not. Yeah, well, for this machine, I just want to reduce the torque ripple, so the operation speed and the operation current is relatively not is relatively low, so the thermal is not a huge problem in this machine. But if we need some under the heavy load condition, yes, I think we need to verify the thermal part for the machines.
Okay, thank you. Very clear. Next question is, have you already investigated the shaft flux leakage due to asymmetric fields by 3D calculation of your optimal consequent pole machine in consideration with the frame? This could be an important issue for bearing in an industrial application.
Yes, this is a very good question here. Actually, for the consequent pole machine, they all have the problem of the shaft flux leakage. And to reduce this problem, here in the modular structure, they try to use the same amount of north magnet and south pole magnet, so they can reduce the flux leakage. But for my machine, yes, the flux leakage exists, and I verified it with the 3D model in the GMAG. Mm, but this is also related to some other parameters like the air gap length, like the something else. So yeah, I'll find some way to reduce it. Yeah, thank you.
Thank you, G. Next question is the issue of torque ripple associated to machine control and drives, like time harmonics of the armature currents?
Yes, for the control side, actually, yes, I think since in the simulation, we use the standard sinusoidal waveform, the sinusoidal current waveform. So we just ignore the current harmonics. But in the control side, here we can see we have the even order harmonic of back EMF, and it will lead to the even order harmonics in the current. So that will in turn cause the more torque ripple in the real in the application. So that's what I need to reduce the unbalanced back EMF, and I want to reduce the torque ripple here. Yes.
Thank you. Next question is about the topology method you used. Do you plan to run topology optimization for getting new shape geometry? So topology optimization is a feature, optimization feature in GMAG. I don't know if you have tried it. I think this question is related to that.
So what do you mean? Do you mean the optimization process?
Yeah, we have in GMAG, you have parametric optimization and topology optimization. So
Yes.
I think the genetic algorithm is part of the parametric parametric optimization.
Yeah.
I think you could check the topology optimization to have different shape, or to use GMAG to find some different shape.
Yes, I think this is all of this optimization method can be utilized here. Here, I think it's just a tool to verify the principle behind the pole shape. Here, I mean, since I mean, the principle is to move the phase of PM torque ripple and the reluctance torque ripple to counteract with each other. So no matter what the method we use, we should find this phenomenon here. We should verify this phenomenon. So Here, I think the genetic algorithm I'm just familiar with this method, and it's very useful method here. So I just try to want to select this method. Yes, we can try some other method like the parametric, but probably the parametric method will cost more calculation. Just probably, yeah. But they should have the same results, I think.
Okay, thank you.
Thank you.
We have another question, which is how easily these magnets get demagnetized during transient and high temperature?
Yes, this is a concern, major concern in the heavy load condition, especially in the electric vehicle applications. But in here, I didn't analyze it. For this flux distribution figures, we can see the magnet is the status is quite good. They don't have the demagnetization risks here. But under the heavy load condition, due to the armature reaction, they will have the risks of the demagnetization. And especially for the consequent pole structure here, we know it has a larger inductance. That means the armature reaction for the consequent pole machine is larger than those like the SPM machine. So it will cause this is a major concern. I think it's a major concern in the heavy load condition. Yes. Thank you.
Okay, thank you. Thank you, Ji. So I think we have covered all the questions now. Yeah, I think it's fine. So thank you very much again for your presentation and answering all of your questions.
Thank you
It was
very
a
much.
pleasure to welcome you to this GMAG user conference. I will slightly share my screen again for introducing the next one. So G, I think you have to make me presenter again. Can you right click on my camera, or there is the option?
Yeah, I have just stopped the sharing my screen.
Okay, anyway, I think it's fine. So yeah, it will be time for the next presentation. In 5 minutes, we'll start the presentation from NIDEC PSA e-motor about calculation of electromagnetic forces in centric and eccentric permanent magnet synchronous reluctance machines. So feel free to go back to the agenda in Whova to connect to the next session. Thank you very much, everyone, for attending this presentation, and thank you again, G, for your presentation.
Thank you, Hussein. Yeah.
Have a nice day. Bye bye.
Bye. Have a nice day, you too.